Now I am planning to discuss only three problems, but three problems from based on three different types of convergences. One is LP convergence, which involves expectation. Another is convergence in distribution. Another is convergence almost everywhere. So these are the three problems, but it is interesting to note that this LP convergence, in this case we have taken P equals to 3, can be proved very easily using two things. One is simple school level algebra, another is simple probabilistic idea, or rather the idea of or the simple theory on expectations. So although it seems sometimes that the convergence problems might be difficult, but in many cases it's not so difficult, and even we can prove them using very elementary properties or elementary results. On the other hand, the convergence in almost everywhere mode, that is almost sure convergence, requires little bit of technique that we are going to see. Sometimes it seems obvious, but the proof is not really very easy to do immediately. So we have to consider, or we have to apply few tricks or few more results in probability theory. As for example, most importantly and most commonly used, that is Borel-Cantelli lemma in proving some almost everywhere convergence. We are going to prove that. We are going to discuss this thing based on three different problems. Today we will discuss few problems on mostly some law of large numbers, maybe central limit theorem and so on. Let's start with a very simple problem, but very interesting. This problem is due to Hoel-Portstone, from the book by Hoel-Portstone. So it says that suppose x1, x2 and so on are identically and independently distributed random variables with mean 0 and finite variance sigma squared. Sigma squared of course is greater than 0. So up to this we usually know that whenever, in many cases, we have random variables where we assume that the mean to be 0 and variance to be some finite quantity. In this case it is sigma squared. Now assume that x1 has finite third order moment. Now when we assume x1 has a finite third order moment, that means all the variables, each of these x1, x2 and so on, all these variables has finite third order moment because they are identically distributed. So assuming that the third order moment exists, is finite, we have to show that limit n goes to 0, expectation of Sn by sigma root n whole to the power 3 equals to 0. That is, Sn by sigma root n converges to 0 in LP. Now naturally P is equals to 3. So this gives us some idea about the LP convergence or L3 convergence. Let's see how we can prove this result. Now whenever we are trying to prove any result, let us first look at the expression or at the main expression around which the main proof will revolve. Now Sn is here the variable of interest or the sequence of interest, and Sn is defined as x1 plus x2 plus up to xn. And note that here we want not only Sn, but we must be interested in expectation of Sn whole cube. So first thing is that we need to know what is the expression for Sn to the power 3, that is x1 plus x2 plus dot plus xn whole cube. So we should start with this algebraic expression. So although this is a problem in the convergence or the convergence in the probability theory, but it starts with a simple algebraic manipulation in deriving few expressions which are essential in order to prove this result. So, and remember, we will use only the properties of expectation here. So the proof is supposed to be very simple. Let's see whether it is really simple or not. But remember, it starts with the algebraic manipulation of Sn cube. Now Sn cube is summation xk, k equals to 1 to n whole cube. If we evaluate this thing or expand this thing, we will have summation k equals to 1 to n xk whole cube, xk cube, plus summation L not equals to k equals to 1 to n xk square into xl, plus summation r not equals to L not equals to k equals to 1 to n xk into xl into xr. So basically the second term has two summations, one over L and another over k, both runs from 1 to n, but L cannot be equals to k. Similarly, the third term has three summations or summation over three suffixes r, L and k. Each of them runs from 1 to n, but r not equals to L not equals to k. So, and if we recall what we are going to prove, we are going to prove something with respect to expectation of Sn cube. So we know that Sn cube is this expression. So just take expectation of Sn cube. But before taking expectation of Sn cube, or rather expectation on both sides, most important thing to note is that x1, x2, they are all IID or independently and identically distributed random variables with expectation of xk equals to 0, variance of xk equals to, in fact, expectation of xk square, because expectation of xk equals to 0. So variance of xk is equals to sigma square, and expectation of xk cube equals to mu 3, because we assume that the finite third order moment and mu 3 is naturally less than infinity. And this is true for every k equals to 1, 2 and so on. So these are the expression for expectation of some expressions with respect to each xk. So now if we take, so now remember the expressions in the expansion of Sn cube, especially the second and third terms. Second term involves xk square xl. So if we take expectation of xk square into xl, xk and xl are independent because k not equals to L. So this is equals to expectation of xk square into expectation of xl, which is equals to 0. And r not equals to L not equals to k. And for that, expectation of xk into xl into xr, all k, L, r are not equal. That means they are all different. So this is equals to expectation of xk into expectation of xl into expectation of xr, because they are all independent, and which is equals to 0 because each expectation is 0. So now this becomes, that means if we take the expectation on both sides, second and third term will contribute exactly 0. So expectation of Sn whole cube equals to, or Sn cube equals to expectation of summation k equals to 1 to n xk whole cube. That means if we expand this whole thing, this will be n into expectation of x1 whole cube, because if we expand this thing, only first term will remain, that is expectation of summation xk cube k equals to 1 to n. Now each xk is again identically distributed, so xk cube must have the same expectation as that of expectation of x1 cube, which is in fact mu 3 in our notation. So expectation of Sn cube is nothing but n times mu 3. So you see, although this expansion of Sn cube is slightly complicated, but ultimately when we take expectation, the expression is so simple, it's just n into mu 3. Hence, if we divide Sn cube by sigma into root n, that is, or Sn by sigma root n whole cube, so there is a power in the denominator of n to the power 3 by 2. So this becomes, and if we take limit n goes to 0, that means limit n goes to infinity, expectation of Sn by sigma root n whole cube equals to, in the numerator there is n into mu 3, and in the denominator there is a term n times root n. So n cancels out, and we are left with one term which is root over n in the denominator. And sigma 3 is finite, mu 3 is finite. So the entire limit becomes 0. So just by taking simple expectation and using the properties of the random variables, or the fact that they are all independently and identically distributed, we can easily prove this result. Now, note one important thing is that although we are dealing with, or we are trying to prove some result related to some convergence in expectations, Hoel Q or L3 convergence, entire proof is done only using expectations. Let us move on to another problem. Suppose, which is a very simple but very important problem. Actually, this will give us an idea of how to evaluate the distribution or asymptotic distribution of few standardized variables. Let us first state the problem, and then I will discuss the implications of this theorem or this problem. Let x lambda be a Poisson random variable with parameter lambda. Lambda is of course greater than 0. Now we want to find the asymptotic distribution, or the distribution of x lambda minus lambda divided by root lambda as lambda goes to infinity. Now remember one thing, that for a Poisson random variable with parameter lambda, expectation of the variable is lambda and variance is also lambda. So if we want to consider the standardized variable, that means x variable minus its mean by standard deviation, it will turn out to be x lambda minus lambda divided by square root lambda for a Poisson random variable. And we are going to find out the distribution of this standardized variable when lambda goes to infinity. So how to proceed this problem? As we know that in order to find, there is a one-to-one correspondence between the distribution function and the characteristic function. So one easy way to start this kind of problem is to use the characteristic function. There might be other ways also, but it is always easy to apply characteristic functions in order to prove or in order to evaluate the asymptotic distribution of few standardized variable. So we will use the characteristic function to evaluate the asymptotic distribution of standardized Poisson variable. Now what is the characteristic function? We know expectation of e to the power itx is the characteristic function of the random variable x. Here the random variable is the standardized variable. That means the random variable we consider is x lambda minus lambda divided by square root of lambda. So phi t equals to, that is the characteristic function of the standardized Poisson variable, is equals to expectation of e to the power it into x lambda x suffix lambda minus lambda by square root of lambda. So a little bit of algebraic manipulation will guide us, that will say that if we expand the power of e, or the exponent part, there is a constant minus I into t into square root of lambda. So e to the power minus it square root of lambda comes outside the expectation. So we are left with expectation of e to the power it x or x lambda by square root of lambda. Now if we replace t by square root of lambda, and little bit of manipulation will give us this expression of the characteristic function, which is in fact we can write, or we can simplify to exponential lambda e to the power it by square root of lambda minus 1 minus it by square root of lambda. Now as lambda goes to, so now we want to find out this expression as lambda goes to infinity. So let us write down, so phi t, if we want to expand this thing, so you see one slightly complicated, it looks slightly complicated but not really very difficult. Note one thing, inside the exponential there is another e, another exponent part. So the easiest way to evaluate this entire expression on the right hand side is to expand the exponent part, or e to the power it by root over lambda inside the bracket or inside the exponential. So phi t becomes e to the power or exponential of lambda. Just expand this term 1 plus it by square root of lambda plus I square t square by 2 factorial into lambda plus I cube t cube by 3 factorial into lambda into root over lambda plus dot dot, and whatever is left as the other terms, that is minus 1 minus it by square root of lambda. Now we will just simplify this expression. It gives us this. Here if we look at this term, here there is one cancellation is there, and after simplifying we get e to the power minus t square by 2 factorial minus I into t cube by 3 factorial into square root of lambda and plus whatever terms are there. But now the rest of the terms involve one lambda or some power of lambda in the denominator. So as lambda goes to infinity, this entire quantity will go to e to the power minus lambda square, e to the power minus t square by 2. Now, what is the meaning of this? That here we are taking limit as lambda goes to infinity. That means limit lambda goes to infinity of phi t equals to limit lambda goes to infinity into the exponential of whatever term is there, which is equals to e to the power minus t square by 2, because all the terms will vanish which involve some lambda to the power something in the denominator. Now the right hand side, that is e to the power minus t square by 2, is nothing but the characteristic function of a normal 0 1 random variable. Hence, by uniqueness theorem of characteristic function, we can immediately say that the standardized Poisson variable follows a normal distribution or converges to tau, where tau follows normal 0 1 in distribution. So this is actually basically this is a technique that whenever we have some standardized variable, that is variable minus mean by its standard deviation, we can think one way of evaluating or deriving the asymptotic distribution is to take the characteristic function or to find the characteristic function and then try to see what happens to this characteristic function as in the asymptotic sense, like in this case lambda goes to infinity, or in some case depending on the sequence of variables as n goes to infinity. If we see that we can get some function which is the characteristic function of some known variables, then we can immediately claim that the limiting distribution is nothing but the distribution corresponding to that limiting characteristic function. So this is a nice way of evaluating or deriving the asymptotic distribution of few standardized variables, or in general this technique is a nice technique to apply asymptotic distribution for some other variables or other sequence of variables, or the function of sequence of random variables. Our next problem is again very simple, but if we recall that the first problem we discussed is a problem on convergence with respect to some moments. Second problem we discussed is a convergence of a distribution, convergence in some distribution or with respect to the distribution function, which involves, of course, the proof of course involves characteristic functions. Now let us consider another problem that involves almost sheer convergence or almost everywhere convergence. Let xn be a sequence of random variables such that xj's are uncorrelated. That means covariance between xi and xj equals to 0 if I not equals to j, and variance of xj is sigma square less than capital M, which is less than infinity, for all j equals to 1, 2 and so on. That means this variance of sigma square is bounded by a finite number. This condition is essential, as we will see in the proof of the result, which is that is we have to show under this condition, we have to show that Sn minus expectation of Sn by n almost surely goes to 0 as n goes to infinity. Now first, without loss of generality, we assume that expectation of xj equals to 0. There is no harm in considering this assumption, because we can just do some kind of origin change to make this expectation 0. Now, so let us assume that expectation of xj equals to 0 for all j, so that variance of Sn is nothing but expectation of Sn square which is less than equals to n into m. It can be easily seen that expectation, because if we expand this by some square term, we will get it, or we can directly get it from variance of Sn, because variance of Sn is nothing but variance of summation xi I equals to 1 to n, which is again summation variance of xi plus double sum I not equals to j, covariance between xi xj. And since xi's are uncorrelated, so covariance term will vanish. So we are left with only variance of Sn equals to summation variance of xi I equals to 1 to n, that means m times sigma square. Now as we know that sigma square is less than m, so we can immediately write that this is less than n into capital M. Now it will intuitively start, so this entire proof involves Sn. So it is clear that we have to start with Sn, which in fact we did. Now let's try to apply the Chebyshev's inequality, which we know for a long time. It says that for epsilon, and if we apply Chebyshev's inequality for every epsilon greater than 0, we immediately write probability modulus of Sn greater than n epsilon is less than equals to mn by n square epsilon square. Because there is a term sigma square, and the sigma square is bounded by nm, so eventually this gives us m by n epsilon square. But the important thing is that if we take the summation on both sides, the right hand side will convert, because m is a finite quantity. So if we take the summation, m by epsilon square come outside, and it will remain as 1 summation n equals to 1 to infinity 1 by n, which is in fact diverges. So this is the technique that we should remember. So now let's start with, so actually when we start with Sn, actually we didn't get the result, but we have a feel what is happening. So let's change little bit, and let's start with Sn square by n square. So again Chebyshev's inequality to the subsequence Sn square and summing over n, we have exactly similarly we can have. Now remember, in the suffix this n square we should replace by, in the suffix n, initially it was n in the previous case, now it is, we replace it by n square. So we have to replace everything by n square, all the n by n square. That means the right hand side becomes summation over n, m by n square epsilon square. Now this quantity is finite, this quantity is convergent. So by Borel-Cantillo lemma we can immediately say that probability modulus of Sn square is greater than n square epsilon infinitely often is equals to 0. This is the direct consequence of Borel-Cantillo lemma. So immediately we can say that Sn s suffix n square by n square converges to 0 almost everywhere. But remember one thing, we have to prove Sn by n, not Sn square by n square, but we have already proved this thing for Sn square by n square. Let's call this as equation 1. Now, it is enough to show that Sk does not differ much from the nearest Sn square to make any really significant difference. So in that case, if Sk and Sn square are very close to each other, then I think the proof will be complete. So in order to prove this thing, let us define Dn, which is modulus of Sk minus Sn square, maximum over n less than equals to k less than n plus 1 whole square. Maximum over n square less than equals to k less than n plus 1 whole square. So now little bit of algebra or algebraic manipulation will give us immediately expectation of dn square is less than equals to 2n into modulus of Sn plus 1 square minus Sn square whole square, which is nothing but 2n into summation j equals to n square plus 1 to n plus 1 whole square into variance of xj, which is less than equals to 4n square into n. Little bit of algebraic manipulation will give us this result. Now again we apply Chebyshev's inequality to get probability dn greater than n square epsilon is less than equals to, as we got just now, 4m by epsilon square n square, which means that is again if we consider summation on both sides over n, the right hand side will converge, and hence again by applying Borel-Cantillo lemma, it is clear that dn by n square goes to 0 as almost everywhere. Now using 1 and 2, we can write that modulus of sk by k is less than equals to modulus of Sn square plus dn by n square, whenever for n square less than equals to k less than n plus 1 whole square. And of course now the proof is complete, it's obvious, because the right hand side we have shown that each term converges almost surely almost everywhere to 0, because immediately we have shown that dn by n square goes to 0 almost everywhere, and previously we have seen that Sn square by n square goes to 0 almost everywhere. So the right hand side goes to 0 almost everywhere, and hence modulus of sk by k, or in other words Sn by n, goes to 0 almost everywhere. So you see here that we actually did not get the proof immediately when we considered the sequence Sn by n, but we started to explore what happens to the sequence Sn square by n square, and we try to see that if we can find out that k is very close to the nearest Sn square, then we are done. Actually, this is a very nice technique, and in this proof we have applied Chebyshev inequality, but most importantly Borel-Cantillo lemma, in order to prove the almost everywhere convergence. And so we can claim now that the proof is complete. So we have seen that we have discussed three problems. First one is based on LP convergence, where we have taken in this problem AP equals to 3, and the proof is very simple. Just simple evaluation of a cube function and taking the expectations, we have proved this result. It's extremely easy, as you have seen. Second one is very easy. At the same time, it is important to remember, or important to note few things. One is that convergence in distribution we have proved through characteristic function, because of the simple fact, the well-known fact that characteristic function and distribution function has a kind of one-to-one relationship, and there is a uniqueness theorem. But this opens a broad area in the sense that whenever we have to prove some results for convergence in distribution, one important technique that we have learned is to use characteristic function. So try to apply this technique, or try to evaluate the characteristic function and see whether it matches with our common knowledge of characteristic function of some known random variable. And since there is a uniqueness theorem for characteristic function, we can immediately apply that theorem and find the distribution function of the convergent random variable. So this is a very important technique. Next came the almost everywhere convergence. We have seen that this is somehow intuitively clear, but the proof requires a little bit of technical things. As for example, it is not immediately clear what happens when mod Sn or Sn by n sequence, but in that case we have moved on to a subsequence. So when we study a sequence, we can sometimes continue the study through a subsequence, and then prove a result, and then try to show that the previous one and the new one are very close to each other. In that sense, we can prove the almost everywhere convergence. And as we have already noted that Borel-Cantillo lemma plays a very, very important role in proving almost everywhere convergence, along with the knowledge of analysis, or rather the convergence of sequences and series of real numbers. So coupled with all these things, we have been able to prove for the almost shear convergence corresponding to this given problem, but we can apply the same technique to many other problems in order to prove almost everywhere convergence.